Module 1, Lecture C, Tensors Fundamentals. By the end of this lecture, you will be able to create and manipulate PyTorch tensors using common factory functions and indexing operations. Explain how tensor shapes, dtypes, and devices affect performance and correctness in PyTorch 2.10.0. And perform basic numerical operations on tensors and debug common shape and device mismatch errors. Creating PyTorch tensors, tensor creation basics. In PyTorch, tensors are the fundamental data structure that everything else is built on. They generalize scalars, vectors, and matrices to any number of dimensions. So a single number is a zero-dimensional tensor, a list of numbers is one-dimensional, and an image made of pixel values is two-dimensional. A collection of images forms a higher dimensional tensor, such as 3 or 4 dimensions, depending on how the data is organized. PyTorch offers convenient ways to create these tensors with specified data, shape, and properties, so they are immediately ready for computation and model training. In PyTorch, you usually create a tensor from existing data, or by specifying its shape, such as turning sales numbers or simulation coordinates into a structured format. You must tell PyTorch how to interpret this data, including its dimensions, how elements are arranged, and what numerical type to use. Built-in factory functions make reasonable default choices based on your input, but still let you customize these details. This flexibility helps you quickly convert raw data into tensors that are ready for neural networks, data pipelines, or scientific computations. As you gain experience creating tensors, you will start planning their shapes and dimensions before you write any code. For example, you might use a one-dimensional tensor for a single user's features and a two-dimensional tensor for a batch of users. Or in time series forecasting, you might organize data by time steps, variables, and sequences. Choosing appropriate tensor shapes from the start makes indexing, reshaping, and other operations much easier and helps prevent bugs. In this way, carefully planning your data as tensors provides a solid foundation for all your PyTorch computations. Python code, tensor creation basics. This lesson introduces the basics of creating tensors using PyTorch. You will see how to make new tensors, check their shapes, and understand their data types. The focus is on recognizing how tensors are structured and how to inspect their properties. You will also practice simple indexing to access specific elements within a tensor. By the end, you should be comfortable creating and examining basic tensors. The line that begins with an exclamation mark is a shell command used to install PyTorch and its related libraries. It is usually run in a Jupyter Notebook or similar environment to make sure PyTorch, Tor Vision, and Tor Audio are available. These libraries are important because they provide the tools for creating and working with tensors, which are at the core of PyTorch's functionality. We begin by importing the PyTorch library so we can work with tensors. This import gives us access to PyTorch's tools for creating, modifying, and using tensors. Tensors are the core data structures used in many machine learning and deep learning tasks, so having PyTorch available is essential for these operations. We start by printing the version of PyTorch being used so we can clearly document the environment in which the code runs. This matters because different PyTorch versions may change features, behavior, or bug fixes. Knowing the exact version helps ensure that results are reproducible and that others can match the same setup when they run the code. We create a one-dimensional tensor in PyTorch from a list of floating point numbers that represent monthly sales figures. Using a tensor lets us take advantage of PyTorch's efficient numerical computation tools and makes it easier to connect this data to machine learning workflows. By providing the data as a list, we preserve the original values, their order, and their type when the tensor is created. We begin by viewing the contents of the monthly sales tensor to get a quick sense of the data. Then we check its shape, which tells us how many elements it has along each dimension and helps us understand its structure. Finally, we examine the data type of the tensor elements to ensure they are compatible with later operations and to know how the data is stored in memory. We use PyTorch to create a two-dimensional tensor that stores a small set of coordinates. It is built from a list of lists, where each inner list holds two floating point values. In this example, the first pair represents the coordinates 0 and 1, and the second pair represents 2 and 3. Organizing the data in this grid-like tensor form makes it convenient to work with spatial coordinates or other information that naturally fits into a matrix structure, such as image data. We first display the contents of the two-dimensional tensor, called chords, so we can see the actual values it holds. Then we display its shape, which tells us how many rows and columns it has. Together, these steps help us understand both the data stored in the tensor and how that data is organized. In this example, we use PyTorch to create a tensor filled with zeros, specifying a shape of 2 by 3, so it has 2 rows and 3 columns. We also choose the float32 data type, meaning each value is stored as a 32-bit floating point number, which is common for numerical work. This kind of zero-filled tensor is useful when you need a specific shape and type, ready for later data or computations. We use a PyTorch function that creates a new tensor filled with ones, matching the shape and data type of an existing tensor called zeros grid. This lets us quickly generate a tensor that is structurally identical to another, but with all values set to 1. Doing this helps maintain consistent dimensions and types across related tensors, which is important for operations that require them to align correctly. We first print the shape of a tensor filled with zeros to confirm its dimensions. Then, we print the shape of a tensor filled with ones that was created to match the zeros tensor. Comparing these shapes shows how factory functions can generate tensors with specific dimensions. This ensures consistency when creating and working with multiple tensors in related operations. In this example, we use PyTorch to create a one-dimensional tensor with a sequence of numbers from 0 up to, but not including, 5. The numbers increase by 1 each time, so the step size is 1. We also set the data type to a 64-bit integer, so each value is stored as an integer with that precision. This approach is a convenient way to generate numeric ranges directly in tensor form. We begin by printing the entire tensor called steps to quickly check the sequence of numbers it contains. After confirming its contents, we show basic indexing by retrieving the first element in the sequence. We then use a method that converts this tensor element into a regular Python number. This makes the value easier to use in later calculations or to display in a more familiar format. Slicing lets us extract a portion of a tensor without changing the original data. In this example, we take elements from index 1 up to but not including index 4 to form a new tensor. This new tensor contains the second through fourth elements of the original. Using slicing in this way is a convenient method to work with just a subset of the tensor's values. We print the sliced tensor to confirm that the slicing operation worked correctly. This sliced tensor is a subset of the original range tensor, so viewing it lets us check both its values and its shape. By examining the printed output, we can verify that the elements and dimensions of this new tensor view match what we expect from the slice. This script introduces basic tensor operations in PyTorch by first checking the library version, then creating simple one-dimensional and two-dimensional tensors and examining their shapes and data types. It shows how to build tensors from lists, such as monthly sales or coordinate pairs, and how to inspect their structure. The script then uses factory functions to create grids of zeros and ones with specified shapes, emphasizing how these functions control tensor dimensions. It also demonstrates how to generate a range of values, access individual elements with indexing, and extract subranges with slicing, while confirming the resulting shapes. Overall, it provides a concise overview of creating, inspecting, and indexing tensors in PyTorch. Random and constant tensors. In deep learning, random and constant tensors are basic tools for quickly generating structured data. Random tensors, typically sampled from uniform or normal distributions, are essential for initializing neural network parameters and simulating noise. Constant tensors, which repeat values like zeros or ones, are used to build masks or define initial states. By understanding how to use both types, you can set up experiments efficiently and control model behavior in a predictable way. When working with random tensors, you must consider both their shape and the statistical properties of their values. For example, initializing model weights for image tasks requires random tensors whose dimensions match the filters, input channels, and spatial size. The distribution you choose for these random values affects learning stability, because extreme values can harm gradient behavior. Random tensors are also used to simulate real-world variability, such as sensor readings or financial time series. To make experiments reproducible and easier to compare or debug, you should set a random seed so the same sequence of random values can be generated again. Constant tensors are important because they provide fixed structure and reference points in many workflows. Tensors of zeros can represent empty images or initial hidden states, while tensors of ones can act as baseline inputs or a way to broadcast a single value. In tasks like image segmentation, constant tensors serve as masks that mark which elements are valid and which, such as padded tokens, should be ignored. In simulations, they capture fixed conditions like boundaries or standard pressures. By combining these constant tensors with random tensors, you can build complex setups that remain both realistic and manageable. Python code, random and constant tensors. This script demonstrates how to create random and constant tensors using PyTorch. It provides simple examples so you can see the difference between values that are generated randomly and values that stay fixed. Run each part of the script in order and pay attention to how the outputs change or remain the same. This will help you understand basic tensor creation and behavior in PyTorch. This line is a comment explaining that if PyTorch is not already available in a Colab environment, you can run a command to install it, along with Torch Vision and Torch Audio. It specifies the CPU versions of these packages. The purpose is to make sure all required libraries are installed so the rest of the script can run correctly, even in environments where they are not pre-installed. We begin by importing the PyTorch library, which we need for creating and working with tensors and for performing any operations in PyTorch. After that, we check and print the version of PyTorch that is currently installed. Knowing the version helps us confirm compatibility and can be important when troubleshooting, since different versions may behave differently or offer different features. Setting a manual seed in PyTorch makes its random number generation deterministic. This means that each time you run the program with the same seed, it will produce the same sequence of random values. Doing this is important when you need to debug your code or reliably reproduce results across different runs. We start by checking whether a graphics processing unit is available, and if it is, we set the computation device to use it. Otherwise, we fall back to the central processing unit. This choice is important because using a graphics processor can greatly speed up work with large tensors and complex operations. Finally, we print which device is being used, so we have immediate confirmation of the environment setup. We create a small random tensor, in PyTorch with 2 rows and 3 columns, where each element is drawn from a uniform distribution between 0 and 1. This means every value in that range is equally likely to appear in any position of the tensor. We store this tensor in a variable, and then print its shape to confirm that it has the intended 2 by 3 dimensions. This quick check ensures the tensor was created correctly before using it in further computations. We create a small 2 by 3 tensor using PyTorch's random normal function on the chosen device, such as a GPU if one is available. The entries of this tensor are drawn from a normal distribution, so they are centered around 0 with a standard deviation of 1. We then compute the mean of all the tensor's values to check that they are roughly centered around 0, as expected. Finally, we print this mean value to observe the result. We create a constant tensor of zeros using the zeros function from the Torch library, specifying a shape of 2 by 3. This tensor is allocated on the previously chosen device, which may be a graphics processor if available, or the central processor otherwise. After creating it, we print the first row to confirm that all its values are 0. We use PyTorch to create a constant tensor filled with ones, specifying that it should have 2 rows and 3 columns. This tensor is allocated on the available device, which may be either a graphics processor or the central processor. To confirm that it was created correctly, we print the first row and check that all its values are ones. We define a custom value of 0.5 and use it to create a tensor with 2 rows and 3 columns, using PyTorch's method for filling a tensor with a single value. This tensor is allocated on the previously chosen device, which may be either the CPU or the GPU. To confirm that it was created correctly, we print the first row and see that every element is set to the value 0.5. This example shows how to access a single element in a tensor. We take the first value from a random uniform tensor by indexing the position in the first row and first column. That element is then converted to a floating point number and printed for easier reading. This illustrates how to retrieve and inspect individual tensor values, which is helpful for debugging or analyzing specific entries. The code first checks whether the 2 tensors, one filled with uniform random values and the other filled with ones, have the same shape, because tensors must match in shape to be added element by element. If their shapes match, it adds them together and stores the result in a new tensor called added. It then prints the first value from this result, converting it to a floating point number for easier reading. If the shapes do not match, it instead prints a message explaining that the tensors cannot be safely added because their shapes are incompatible. The code moves a tensor from the GPU to the CPU so it can be printed safely. Tensors stored on a GPU are not always directly accessible to standard printing tools. By transferring the tensor to the CPU first, it becomes compatible with normal output functions. This allows us to view its contents without running into access or compatibility issues. This script shows how to create random and constant tensors in PyTorch while managing devices and reproducibility. It begins by checking the PyTorch version, setting a manual seed, and choosing either a GPU or CPU depending on what is available. The code then creates 2 by 3 tensors from uniform and normal distributions, reports their shapes and mean values, and builds constant tensors filled with zeros, ones, and the value 0.5, printing sample rows. It demonstrates basic tensor indexing by accessing the first element of the uniform tensor and checks that tensor shapes match before adding them, then prints a sample result. Finally, it moves the uniform tensor back to the CPU before printing, illustrating how to safely handle tensors across different devices. From NumPy arrays. In many projects, It is common to start with NumPy arrays and then convert them into PyTorch tensors. NumPy is widely used for numerical data in data science and scientific computing, so this conversion lets you reuse existing data and workflows. By turning arrays into tensors, you can take advantage of PyTorch features like automatic differentiation and GPU acceleration without redesigning your data pipeline. In effect, you are placing familiar NumPy data into a PyTorch-compatible container while keeping the same structure, which makes it easier to move from data analysis to building deep learning models. When you convert a NumPy array to a PyTorch tensor, the shape stays the same, so a two-dimensional array remains two-dimensional, and the data type, such as integers or floats, is also preserved. However, you still need to ensure the type matches what your PyTorch operations expect, for example, single precision floats in many neural network tasks. The conversion often uses shared memory, so changing the array can change the tensor and vice versa. This is efficient for large datasets, but requires careful handling when mixing NumPy and PyTorch code. In many real projects, it is common to convert NumPy arrays into tensors during data loading and pre-processing. You might first clean and normalize time series or structured data in NumPy, or process images with a library that outputs NumPy arrays, and then turn these arrays into tensors for model training. This approach is used in areas like forecasting, computer vision, finance, and social sciences. Converting NumPy arrays to tensors lets you move smoothly from exploratory analysis to using PyTorch's advanced tools for high-performance predictive modeling. Python code from NumPy arrays. This script demonstrates how to convert NumPy arrays into tensors with an emphasis on understanding shapes, data types, and devices. As you run each cell in order, pay attention to how the array shape is preserved, how different data types are handled, and how tensors can be placed on different devices. The goal is to help you see the relationship between NumPy data and tensor representations in a clear, step-by-step way. The commented line is a reminder to install PyTorch and its related libraries before running the script. You need PyTorch, along with Tor Vision and Tor Audio, in your environment. These libraries are essential because they provide support for tensors and the operations performed on them. Without them, the main functionality of the script will not work. We begin by importing a few key libraries that we will use throughout our work. The operating system library lets us interact with the system, for example, to work with files or environment settings. The random library allows us to generate random numbers, which is helpful for creating random data or setting random seeds. Finally, we import NumPy, a powerful tool for numerical computing that makes it easy and efficient to create and manipulate arrays. We first set the random seed for Python's random module to 42, so that any random numbers it produces will be the same each time the program runs, which helps with reproducibility. We then set the random seed for NumPy's random number generator to the same value for the same reason. Using the same seed in both places ensures that all random operations, whether from Python's standard tools or from NumPy, behave consistently across different runs of the code. The script begins by trying to import the PyTorch library inside a protected block so it can catch any import errors. If PyTorch is not installed and the import fails, the program immediately stops by raising a system exit with a clear message that PyTorch is required. This approach prevents the rest of the code from running in an invalid state and avoids confusing errors later in the execution. This line displays the version of PyTorch that is currently installed. Knowing the exact version helps you check compatibility with other tools and libraries. It is also useful for debugging, because different PyTorch versions can have different features or behaviors. Verifying the version can therefore save time when diagnosing issues or sharing your setup with others. We begin by creating a small NumPy array of floating point numbers arranged as a 2x2 matrix containing the values 1, 2, 3, and 4. We set its data type to float32, so the values are stored as single precision floating point numbers. This choice is important because it prepares the array for later conversion into a PyTorch tensor, while keeping the numerical precision and compatibility needed for further operations. We first check the shape and data type of the NumPy array to understand its structure before converting it to a PyTorch tensor. Printing these attributes lets us confirm that the array matches the expected dimensions and type. This verification step is important to ensure a smooth conversion process and to avoid issues in later computations. You can convert a NumPy array into a PyTorch tensor using the fromNumPy method in PyTorch. This method creates a tensor that shares the same underlying memory as the original NumPy array. As a result, any change you make to the tensor will also change the NumPy array, and changes to the array will affect the tensor. This is useful when you want to use PyTorch's features while still keeping a direct link to your original NumPy data. This line displays the tensor's shape, data type, and device after converting it from a NumPy array. It lets you confirm that the tensor has the expected dimensions, that its elements have the correct type, and that it is stored on the intended hardware. In short, it is a quick check that the NumPy to PyTorch conversion preserved the tensor's structure and key properties. We change the first element of the tensor, setting it to 10, to show that the tensor and the original NumPy array share the same underlying memory. When we modify the tensor, the corresponding value in the NumPy array is updated automatically. This behavior illustrates that both data structures are viewing and changing the same data rather than keeping separate copies. After changing the tensor, we print the value in the first row and first column of the original NumPy array and see that it has also changed. This shows that the tensor and the NumPy array share the same underlying memory. The reason is that the tensor was created directly from the NumPy array, so modifying one automatically updates the other. When we use the PyTorch tensor creation function on a NumPy array, it makes a separate copy of that array's data. This new tensor does not share memory with the original NumPy array. As a result, any changes made to the tensor will not affect the NumPy array, and changes to the NumPy array will not affect the tensor. This allows you to work with each data structure independently. We change the NumPy array by setting the element in the first row and second column to 20. This edit is used to show that the tensor we created earlier is independent from the NumPy array. Because they do not share memory, the tensor does not change when the NumPy array is modified. This confirms that the tensor remains unaffected by later updates to the original array. We first print the value at row 0, column 1 of the NumPy array to see its current contents. Then we print the value at the same position in the separate tensor, using a method that extracts its single numeric value. Comparing these outputs shows that the tensor's value has not changed, even if the NumPy array was modified. This demonstrates that the tensor does not share memory with the NumPy array and remains independent. The code uses a built-in PyTorch function to check whether a CUDA-capable GPU is available. This check tells the program if it can run computations on the GPU instead of the CPU. Knowing this is important because using a GPU can greatly speed up processing. This is especially helpful for large datasets or complex models that require a lot of computation. The code first checks whether a CUDA-capable GPU is available. If it is, the tensor used for computation is moved to the GPU to take advantage of faster processing. If no GPU is available, the tensor is kept on the CPU instead. This strategy lets the program run on different machines while automatically using the best available hardware for performance. The code prints the device and shape of the final tensor to confirm where it is stored and how it is structured. Checking the device tells you whether the tensor is on the CPU or GPU, which is important for making sure computations run on the intended hardware and can affect performance. Checking the shape quickly verifies the tensor's dimensions and helps you confirm that the data has the expected structure. This script shows how a NumPy array can be converted into a PyTorch tensor and how they can share memory. It first creates a float array, turns it into a tensor, and demonstrates that changing the tensor also changes the original array, proving they use the same underlying data. It then creates a separate tensor by copying the array, so later changes to the array no longer affect this new tensor. Finally, the script checks whether a GPU is available, moves the tensor there if possible, and reports the tensor's device and shape to illustrate PyTorch's device management and its interaction with NumPy. Tensor shapes and dtypes, tensor rank and broadcasting. Tensors are organized collections of numbers whose rank, or number of dimensions, tells you how many indices you need to locate a single element. A rank 0 tensor is just a single number. A rank 1 tensor behaves like a vector, and a rank 2 tensor behaves like a matrix. Higher rank tensors can represent more complex data, such as a rank 4 tensor that stores batches of color images with dimensions for batch, color channels, height, and width. Understanding tensor rank and what each dimension represents is essential in deep learning, because many operations depend on specific ranks and on the meaning of each dimension, such as batch size or spatial resolution. Broadcasting lets you apply operations to tensors with different shapes by conceptually expanding them without actually copying data. It lines up dimensions from the end and automatically stretches any dimension of size 1 to match a larger size. This makes it possible, for example, to apply a single color correction vector across all pixels in a batch of images efficiently. However, you must pay close attention to which dimensions are being broadcast, because incorrect alignment can produce results that are numerically valid but logically wrong for your task. When working with tensors, it is important to understand how rank and broadcasting interact, because they affect both performance and correctness. Broadcasting can speed up operations by avoiding extra data copies, but unexpected ranks or shapes can cause subtle bugs, such as normalizing over the wrong dimension. In high-rank settings like video processing, you should clearly document what each dimension represents, since changes in rank or shape can alter how broadcasting behaves throughout a model. Regularly checking tensor ranks and shapes before and after operations helps keep models both efficient and logically correct. Python code, tensor rank, and broadcasting. This script introduces the ideas of tensor rank and broadcasting using small numeric examples in PyTorch. It shows how tensor shapes determine their rank and how broadcasting lets tensors with different shapes interact in operations. The explanation also highlights how data types and devices, such as CPU or GPU, affect these tensor operations. Overall, it focuses on how shapes, data types, and devices work together when performing computations with tensors. The command that begins with an exclamation mark installs the PyTorch library along with Torch Vision and Torch Audio, usually in a Jupyter Notebook or similar environment. This ensures that all three libraries are available for use in the script. PyTorch is needed for creating and working with tensors, while Torch Vision and Torch Audio add tools for handling image and audio data. Running this installation step is essential before executing any code that relies on tensor operations and broadcasting. We begin by importing the PyTorch library so we can create and work with tensors and perform computations on them. Having PyTorch available is the foundation for building and running our models. Importing it also lets us check which version is installed, which is important for keeping experiments consistent and reproducible across different systems. We start by setting a fixed random seed in PyTorch, using 0 as the seed value, so that any random numbers it generates will be the same every time the code runs. This makes the behavior of the program deterministic. Having deterministic behavior is important for reproducibility because it allows us to consistently get the same results. This in turn makes it easier to debug the code and verify that it is working as intended. In this step, we create a scalar tensor in PyTorch, which is just a single number, here set to 3.5. This tensor has rank 0, meaning it has no dimensions, as is standard for scalars. By using PyTorch to create it, we can later take advantage of GPU acceleration and other tensor operations in our code. In this example, we create a vector in PyTorch, which is a rank 1 tensor. The vector has 3 elements, 1.0, 2.0, and 3.0. A rank 1 tensor is simply a one-dimensional array of values. This kind of structure is useful when you want to apply mathematical operations across a single line of data. In this example, we create a simple 2x2 matrix in PyTorch, which is a rank 2 tensor made of floating point numbers. This basic two-dimensional tensor is a fundamental data structure in many machine learning tasks. By directly specifying its values, we maintain clear control over the data and make it easier to understand how tensor operations and manipulations will work in later steps. We examine tensor rank and shape using 3 examples: a scalar, a vector, and a matrix. A scalar tensor has rank 0 and an empty shape, meaning it is just a single number. A vector tensor has rank 1, so it is a one-dimensional array, and its shape tells us how many elements it contains. A matrix tensor has rank 2, so it is a two-dimensional array, and its shape shows how many rows and columns it has. Printing rank and shape in this way helps us understand the structure and dimensionality of different tensor types. We use PyTorch to create a batch of tiny RGB images as a 4-dimensional tensor filled with random values. Its dimensions are 2 by 3 by 4 by 4, meaning there are 2 images, each with 3 color channels, and each channel is a 4 by 4 grid of pixels. This structure is common in machine learning, where the dimensions represent batch size, color channels, and the spatial height and width of the image data. We print the rank and shape of the image batch tensor to understand the structure of the data we are working with. The rank tells us how many dimensions or axes the tensor has, and the shape tells us the size along each of those axes. Knowing this dimensionality and size is important to make sure later operations, such as broadcasting or reshaping, are compatible and work as intended. In this example, we create a color gain tensor in PyTorch with 3 values, 0.9, 1.1, and 1.0. These values are used to adjust the red, green, and blue channels of an image. By defining the tensor this way, it can be broadcast across an entire batch of images. This lets us efficiently apply the same color adjustments to many images at once without manually reshaping the data, which is a common practice in deep learning. We first check and print the shape of the images tensor to understand its dimensions, such as batch size, channels, and spatial size. This tells us how the image data is organized before we apply any operations. We then print the shape of the color gain tensor to see how it is structured. Knowing both shapes is important because it lets us confirm that the color gain tensor can be correctly broadcast across the images. This verification helps ensure the broadcasting operation aligns with the intended dimensions and behaves as expected. We use broadcasting to apply a color correction vector to a batch of images without manually reshaping all the image data. In this operation, each image is multiplied by a color gain vector that adjusts the color channels. To make broadcasting work correctly, we reshape the color gain vector so it has one entry for the batch, 3 entries for the color channels, and single entries for height and width. This shape lines up with the channel dimension of the images, allowing the same color correction to be applied efficiently to every image and every pixel. We check the shape of the corrected images tensor to make sure it matches the shape of the original images tensor. This verification step confirms that the broadcasting operation was applied properly. By matching shapes, we ensure that the data dimensions remain consistent and the transformation behaved as intended. We create a 2x3 tensor filled with random numbers and specify that it uses the float32 data type. The choice of data type matters because it controls the precision of the calculations performed on the tensor. Using float32 provides a good balance between numerical accuracy and memory usage. This balance is especially important in machine learning tasks that work with large datasets. We convert an existing tensor from 32-bit floating point to 16-bit floating point to see how the data type affects numerical precision. This is done using a method that changes the tensor's data type. Using 16-bit values can reduce memory usage and may improve performance on some hardware. But it can also lower the precision of the computations. This trade-off between efficiency and accuracy is the main reason for performing this conversion. We first compute the mean of a tensor stored in 32-bit floating point format, which gives the average of all its elements with relatively high precision. We then compute the mean of the same data stored in 16-bit floating point format, where the lower precision can slightly change the result. Comparing these two means shows how the choice of data type affects the precision of numerical calculations. We first print the data type and mean of the tensor that uses 32-bit floating point numbers to see its precision and average value. Then we repeat this for the tensor that uses 16-bit floating point numbers. Comparing these results shows how lowering the precision from 32-bit to 16-bit can change the computed mean, mainly due to reduced precision and increased rounding effects. The code first decides whether to run computations on a graphics processing unit or on a central processor. It uses a built-in PyTorch method to check if a CUDA-capable graphics card is available. If such a card is found, it is selected. Otherwise, the program falls back to the central processor. This approach helps the code automatically use the most powerful hardware available for better efficiency. We first move the images tensor to the selected device, which may be a graphics processor or a central processor, so that computations run on the most efficient hardware available. We then transfer the color gain tensor to that same device. Keeping both tensors on the same device is essential, because they must be co-located to operate on them together without causing compatibility errors. We recalculate the corrected images by multiplying the image data, which has been moved to the selected device, by a color gain tensor. The color gain tensor is reshaped so it broadcasts properly across the image dimensions. This operation adjusts each color channel according to the specified gains. All of this is done on the chosen hardware, such as a CPU or GPU, to take advantage of its computational power. The code reports whether the computation is running on a graphics processor or a central processor and shows the shape of the corrected images tensor. This gives a quick overview of where the work is being done and confirms that the tensor dimensions stay consistent. These checks are important for both debugging and performance optimization. This script demonstrates key tensor operations in PyTorch, focusing on tensor rank, broadcasting, data types, and device management. It creates tensors of different ranks, from scalars to matrices and a batch of RGB images. Then applies color correction to the images using broadcasting with a color gain vector. The script also compares the precision of computations by taking the mean of tensors stored as float32 and float16 to show how data type affects numerical results. Finally, it checks whether a CUDA device is available, moves tensors to the appropriate device, recomputes the corrected images there, and reports the device used along with the shape of the final output. Precision and performance. In PyTorch, the choice of tensor data type affects both accuracy and speed. Double precision provides higher numerical detail, which is useful in scientific computing, but it uses more memory and makes operations slower, especially for large models. Single precision is faster and more memory efficient, so it is usually preferred for deep learning tasks where a small loss in precision is acceptable. Lower precision formats such as half precision are now widely used to speed up deep learning because they use fewer bits, reduce memory usage, and run faster on hardware designed for mixed precision, especially modern GPUs. This efficiency lets larger models or bigger batches fit into the same memory and can significantly accelerate training. However, lower precision has a smaller numeric range and less accurate representation, which can lead to underflow or unstable gradients if not handled properly. To balance performance and numerical stability, most computations are done in lower precision, while critical operations such as those involving loss scaling are kept in higher precision.
The performance of tensor operations depends strongly on how data types match the underlying hardware, whether it is a CPU, GPU, or specialized accelerator. PyTorch version 2.10.0 uses this by optimizing operations for specific data types. On GPUs, single precision and lower precision formats are much faster than double precision, and although the gap is smaller on CPUs, they also benefit from more compact types due to memory and cache effects. Therefore, it is important to balance speed and numerical precision by profiling models and choosing data types that improve performance without losing needed accuracy. Python code, precision, and performance. This script examines how tensor precision affects performance in PyTorch. It compares different data types and simple operations to show how they behave. The focus is on understanding tensor shapes, the devices they run on, and the numerical trade-offs involved in choosing one precision over another. The exclamation mark line is a shell command used to install PyTorch along with Torch Vision and Torch Audio. It is often run in environments like Jupyter Notebooks to make sure these libraries are available to the code. PyTorch is needed for working with tensors, while Torch Vision and Torch Audio handle image and audio data. Installing them first is essential because the rest of the script depends on these libraries to run correctly. We begin by importing three standard libraries: time, math, and random. The time library lets us measure how long operations take, which is important for analyzing performance. The math library offers mathematical functions that may be needed for later calculations. The random library generates random numbers, which can be useful for setting seeds or creating test data. Together, these imports prepare the script to focus on precise and efficient tensor operations. The script begins by trying to import the PyTorch library, which is essential because it depends on PyTorch for tensor operations and performance comparisons. If PyTorch is not installed, the code stops running and clearly informs the user that PyTorch is required for this lesson. This early check prevents the script from continuing without the necessary library and avoids confusing errors later on. To make our computational results consistent and reproducible, we set deterministic random seeds. We first set the seed in the general random number library to 0, so it always produces the same sequence of values each time the program runs. We then set the PyTorch random seed also to 0, so operations like tensor initialization are repeatable. This practice is especially important in machine learning and scientific computing, where being able to reproduce experiments is crucial. This code chooses which device to use for computations, giving priority to a graphics processing unit when one is available. It uses a PyTorch function to check for a CUDA-compatible graphics card. If such a card is found, it runs the computations on the graphics processor. If not, it falls back to the central processor. This setup helps improve performance by taking advantage of the faster processing power of a graphics card whenever possible. This code reports the current PyTorch version and the device being used for computations. It helps you confirm that your environment is configured correctly and that your program is running on the hardware you expect. In particular, it lets you check whether a GPU is available and actually being used, which can have a major effect on performance. This section describes a helper function used to measure how long simple tensor operations take to run. It first moves the tensor to the chosen device, such as a CPU or GPU, and performs a few warm-up operations to stabilize performance. When using a GPU, it synchronizes before and after timing to ensure accurate measurements. The function then records the start time, repeats the operation a set number of times, records the end time, and returns the total elapsed time in milliseconds as a measure of performance. This function measures how long a simple tensor operation takes on either a CPU or GPU. It first moves the tensor to the correct device and runs a few warm-up operations to stabilize performance. If it is using a GPU, it waits for all work to finish before starting the timer. It then records the start time, repeatedly scales and shifts the tensor many times, and again waits for completion on the GPU if needed. Finally, it records the end time, computes the elapsed time in milliseconds, and returns that value. This script uses PyTorch to show how tensor precision affects both performance and accuracy. It runs on a GPU if available, then creates tensors in double, float, and half precision, and repeatedly applies a simple arithmetic operation to each. The results demonstrate that half-precision operations are usually faster, especially on a GPU, because they require less computation. The script then compares how double and half precision accumulate many small increments, revealing that double precision stays close to the exact theoretical value, while half precision introduces noticeable error. Overall, it highlights the trade-off between higher speed with lower precision and slower computation with greater numerical accuracy when choosing tensor data types. Tensor shape transformations. When working with tensors, changing their shape is essential for organizing data efficiently in models. These transformations adjust how data is structured, such as turning an image into a single vector or rearranging dimensions for channels and time steps. Although the numerical values stay the same, reshaping, flattening, and expanding dimensions change how PyTorch interprets and processes the data. Understanding these operations is especially important for complex models that handle high-dimensional inputs like video or audio. When changing tensor shapes, it is important to know whether you are only changing the view or creating a new copy in memory. Simple reshaping or flattening usually reuses the same storage, which is more efficient. In contrast, operations like slicing or transposing can break the original memory layout, so PyTorch may need to create a new contiguous copy, adding overhead. You must also keep the total number of elements the same when reshaping, and only add or adjust dimensions, such as single dimensions for broadcasting, when they match the needs of your specific task. Shape transformations are essential to make sure tensors work correctly across different parts of a model, since each layer may expect its dimensions in a specific order. For example, convolutional layers often use batch, channel, and spatial dimensions, while recurrent layers may use batch, time, and feature dimensions. To align these expectations, you may need to permute or transpose dimensions, stack or unstack along new axes, or concatenate along existing ones, while keeping the underlying data meaning intact. If shapes are misaligned, they can introduce subtle bugs and hurt performance, so building an intuitive grasp of these transformations is important for designing efficient and reliable architectures. This script shows how to perform basic tensor shape transformations in TensorFlow in a way similar to PyTorch. It starts with a two-dimensional tensor representing a batch of grayscale images and prints its shape and data type. The images are then flattened into feature vectors while keeping the total number of elements the same, and this is verified by comparing element counts. Next, a channel dimension is added and later removed using a squeeze operation to demonstrate how dimensions can be manipulated. The script also changes the data type from floating point to integer to illustrate that data type affects memory usage but not shape. Finally, the tensor is reshaped back to its original layout to confirm that the data is preserved throughout these operations. Tensor devices and moves. CPU and CUDA tensors. When working with tensors, it is important to know whether they are on the CPU or on a CUDA device, such as an NVIDIA GPU. Both types represent multidimensional data and support similar operations, but they run their computations on different hardware. CPU tensors use the central processor and system memory, while CUDA tensors use the GPU's many parallel cores. Because of this hardware difference, CUDA tensors can greatly speed up workloads, especially in tasks like deep learning. CPU and CUDA tensors share the same interface, but you cannot freely swap them during runtime without affecting performance and correctness. For speed, it is best to keep tensors on the GPU so you can use parallel processing and avoid costly data transfers. In applications like medical image processing, all related data should stay on the same CUDA device. For accuracy and to prevent errors, every operation must use tensors on the same device, so you need to pay attention to each tensor's device attribute when writing code. When working with tensors, especially across CPU and CUDA devices, it is important to know where each tensor is created and which device it is on. In workflows like recommendation systems, data may start on the CPU, move to the GPU for processing, and then return to the CPU. If tensors from different devices are accidentally mixed, operations such as dot products can fail. By carefully managing when and how tensors move between devices, you reduce errors and keep your computations both correct and efficient. This script shows how PyTorch tensors work on both CPU and CUDA devices, such as in a Google Colab environment. It first reports the PyTorch version and whether CUDA is available, then creates a small tensor on the CPU and displays which device it is on. If a GPU is available, the tensor is moved to CUDA. Otherwise, it stays on the CPU. The script performs a valid addition between two CPU tensors. Then, when CUDA is present, intentionally tries to add a CPU tensor to a GPU tensor to trigger and display an error. Finally, it moves the GPU tensor back to the CPU, multiplies it element-wise with the original tensor, and prints the result's shape and device, illustrating basic device management and error handling in PyTorch. Tensor device transfers. In PyTorch, every tensor lives on a specific device, such as the CPU or a GPU, and you must explicitly move tensors between these devices when needed. You can think of the CPU and GPU as separate memory spaces, so a tensor on the CPU is stored in system memory, while a tensor on the GPU is stored in GPU memory. Before doing operations like matrix multiplications or gradient updates, make sure all tensors involved are on the same device, or PyTorch will raise an error. Understanding this device-specific behavior is essential for correctly managing tensor transfers on both simple machines and multi-GPU systems. When training and evaluating models, managing data movement between devices is essential. Data loaders often create tensors on the CPU, while models may run on a GPU, so inputs must be transferred to the GPU before computing predictions or loss. Later, for tasks like metrics or visualization, you may need to move results back to the CPU because many tools expect CPU data. These device transfers are necessary but can slow down performance, so you should minimize unnecessary movement between the CPU and GPU during the training workflow. Treat the device a tensor lives on as part of its identity, just like its shape and data type. Before doing operations such as addition or concatenation, make sure all tensors involved are on the same device. In practice, you might move data like user features to the GPU at the start of each batch, keep them there while the model runs, and only move final summary results back to the CPU. Being consistently aware of where tensors are stored helps avoid errors, reduces data transfer overhead, and improves performance and debugging in complex models. This script shows how to manage tensor devices in PyTorch by choosing between a CUDA GPU and the CPU. It creates a tensor on the CPU, moves it to the selected device, creates another tensor directly on that device, and adds them together. The result is then transferred back to the CPU for display. The script also demonstrates a common error that occurs when adding tensors on different devices and safely catches and prints a shortened error message. It ends by confirming that the demo is complete, highlighting proper handling of device-specific operations in PyTorch. Common mismatch errors. In PyTorch, you must keep tensors on the same device, or you will get errors when you try to combine them. A common mistake is having model parameters on the GPU while the input data or labels are still on the CPU, which breaks operations like addition or multiplication. This often happens after refactoring code or partially moving a pipeline to the GPU, when some tensors are unintentionally left on the CPU. Always ensure that all tensors involved in an operation are on the same device to avoid these device mismatch errors. Shape mismatches are a common source of errors in tensor operations. PyTorch uses broadcasting to align shapes, but if key dimensions do not match, the operation will fail. This often happens when you add predictions and labels that have different shapes or an extra dimension, or when you change batching or reshape tensors and forget to restore their original form. To diagnose these problems, it is important to understand what each dimension represents, such as batch or time, and ensure they are aligned before performing calculations. In PyTorch, some errors come from a mix of shape, device, and type assumptions that only show up at runtime. For example, you might move tensors to the GPU, but still fail if one tensor has an extra dimension or if a logging function cannot handle a GPU-based loss value. In large projects, these mismatches can pass through many layers and be hard to track down. To reduce these issues, regularly check tensor shapes, keep all tensors in an operation on the same device, and define clear, consistent points where you convert tensors between devices or types. This script demonstrates common tensor mismatch errors in PyTorch, focusing on device and shape issues. It first shows a device mismatch by trying to add a tensor on the CPU to a similar tensor on the GPU, which fails until the CPU tensor is moved to the GPU. It then illustrates a shape mismatch by adding tensors with incompatible shapes and fixes it using broadcasting rules so the operation can succeed. Finally, it creates an extra dimension in a tensor, causing another mismatch when added to the original, and resolves it by removing the extra dimension so the shapes align. Throughout,
The script catches and reports these errors to show how to identify and correct them in practice. In this lecture, you learn to create and manipulate PyTorch tensors using common factory functions and indexing operations. Explain how tensor shapes, dtypes, and devices affect performance and correctness in PyTorch 2.10.0, and perform basic numerical operations on tensors and debug common shape and device mismatch errors. In the next module, Module 2, we will go over Autograd and basics. Thank you for your attention. See you all in the next lecture.